The next presentation is from Zensol Automation. The title of the presentation is How to Apply Vibro-Acoustic Technology to Breaker Diagnosis Online and Offline. Fouad Brikci is the president of the company. He's making the presentation. Zensol is a world leader in the field of acoustic diagnostics for circuit breakers and online tap changers. The company also has extensive experience in conventional maintenance testing applied to high voltage circuit breakers.
Okay, so thank you, Randy. So have a good day, everybody, and thank you to be present for this presentation. So the vibroacoustic testing applied to circuit breakers online, offline. So today's presentation, it's a vibroacoustic method, why and when, how also to use it. And I'm going to present also 8 real cases just to illustrate what we can do with this technology. So in fact, the circuit breaker failure statistics, they can show that most of circuit breaker failures are of mechanical origin. And if you can see, like the failure type, the mechanical, the defective part is in general operating mechanism, and the serial report shows that close to 44% major failures have occurred, and 39%, and for other parts it's around 10%. So 10%. So if you take the total of this, it's more than 50% of the failures are of mechanical origin. So here are the diagnosis methods to detect circuit breakers failures. So I think that everybody is familiar with the contact synchronization. When we have a problem in the contacts, we can see this problem with the timing test. For the bouncing, it's also the timing and the motion test. Bad damping, motion test. Main contact wear, it's a simple micro ohm meter test. Arcing contact wear is the DRM, dynamic resistance measurement. Close and open coil problems, it's also in the timing test with the current coil. Motor problems, first trip, it's also another test. It's a quick test that could be done online also. And for the bad mechanical adjustment, misalignment, bad contact synchronization online, all these kind of problems are could be found by the vibration test. So when we use the timing test, what we can say is that it's a heavy test. It's an intrusive test. It's a very good test, but it's intrusive and it takes time. The motion test, it's also an intrusive test. Dynamic contact resistance measurements, it's an intrusive test. It's a very heavy test, but it's also a good test. And now, so why and when we can use the vibro-acoustic? Because first, it's non-intrusive. It's a unique and repeatable signature. It gives global condition of the breaker. We can compare signatures to highlight problems, and it's also used in preventive maintenance. It's a quick, it can be used online, so it's a quick online detections of unsynchronized breakers. It's an excellent online tool to help the user to decide which breakers are due for a maintenance operation. So it's like the first trip test. It's a quick test, and then with this you can decide which breakers, when you see like the shapes or you can decide if this breaker is due for maintenance or not. And it's also very easy to detect bad mechanical adjustment, and we use it for quality control. So what is the principle? So the circuit breakers generally typical and unique vibroacoustic when the operator and the nature of the sound is an indication of the equipment state. Sorry. Stable breakers always shows consistent vibroacoustic signatures. Any degradation of the breaker induces changes in the vibroacoustic signature. And with a vibroacoustic sensor, which in fact is an accelerometer, we can record this signal the same way as a stethoscope picks up a person's heartbeat. So the method is based on the comparison of the vibration signal to be analyzed and the reference vibration signal. So this reference signal can be a vibration pattern taken at the circuit breaker's commissioning or during a maintenance test, of another phase, or of a circuit breaker of the same family. The analysis is based on the detection of variations between two recordings. So what we do, we try to identify the amplitude differences. We do the same for time differences. And we do a comparison of general shapes of the signals. And also we have mathematical tools, processing tools as envelopes, FFT, etc. So how we use, of course, our instrument like the CBV, which can do the timing, the motion, the DRM, and also the vibration test. And how we do this with an accelerometer and what we call a tap base, where we screw the accelerometer, and this base is sticked on the breakers, and of course on a safe place of the high voltage breaker. So we have to be careful about the sampling time. So we work for the sampling time at 5 or 10 microseconds, so which is a sampling frequency of 200 kilohertz at 5 microseconds and 100 kilohertz at 10 microseconds. So here we have an example of a vibration of a ball bouncing on a plate, which is exactly like a simulation of a breaker contact. So here we have done a recording at 5 or 10 microseconds, which is required for the vibration. The same signal, exactly the same. So the ball bouncing on a plate at 100 microseconds. So this sampling time is okay for timing, for motion, but not for vibration. And here the same signal done at 500 microseconds. And when we do a zoom of the signal, this is the recording at 5 or 10 microseconds, so the signal is absolutely perfect. When you take it at 100 microseconds, so you have a degradation of the signal here that you can see it's broken. And of course, at 500, you have very few points and you start to see nothing. So it's a very, very bad signal. So the accelerometer it's a piezoelectric accelerometer with a wide frequency response. And for the breakers, we use 500 G or plus minus or 1000 G. And it's a very good linearity through the ranges. For your information, we use exactly the same vibration technology for the tap changers. And instead of 500 G and 1000 G, we use 50 G. So this is an example of installation. So here you have phase A, phase B, phase C, and you can see where we have installed the accelerometers that are permanently attached with a glue. And so this way, for 1 year after, you want to do exactly the same testing, so you don't have to remove these mounting bases. They are already there, so So you can do the measurements exactly at the same location from test to test. So here, this is the first case where we have found the adjustment problems on the HPL. Here you can see the two breakers with the same problem. One have broken casing. First has exploded, so it's very hard to find one, and the other produced SF6 alarm. So this one we have been able to understand what was the problem. And here you can notice a very high amplitude on phase B compared to the phase A and C. So here you have phase C 500G, phase B 1300, and phase E 500G. So why the shape and the amplitude is different? So here, when we have dismantled the breakers, these pictures show the impact marks inside the casing of the phase B. And in fact, the mechanism one was touching the carter. So here, these two impacts have been found here. So now, if you want to understand how this works, so you have, this is the HPL breaker, so the carter, and here you can see that the joint here was going up and has broken the carter. So the first has exploded because of this bad adjustment, and the second, in fact, was creating the crack in the carter at this position. So here you can see, in fact, there is a video where we can see here that the SF6 was out, and you can see the bubbles of the SF6 going out. So it was very impressive. So this is the problem of the adjustment. So here, in fact, there is like a value, which is, I can say, magical value that you have to understand and know. And here it's, so in fact, there is a length here that needs to be adjusted very carefully if this is not properly. So the mechanism goes and breaks the carter. And here they are. Here you can see the initial length. It was at 50.3 millimeters. Then we have reduced the adjustment at the value. Here it was at 7.6. It was it was always here you can see like a saturation of the accelerometer of the signal. Here at 9.9, and then finally at the end, it was at here you can see the value at 9.9. This value did not respect the motion and the timing speed of the breaker. So it's why here we have reduced this value to 9.6, and then after, with this good adjustment, thanks to the Vibro-Acoustic signal, we were able to respect the specification of the timing and the motion. Because of course, after, what we do when we have found the problem, thanks to the Vibro-Acoustic, so we were able to do a timing and motion test just to check if the specifications were respected. So here it's after the intervention, you can see that you get the same shapes on all the phases and the same amplitude. Case 2, it was an assembly problem on a HPL 230 kilovolt. here it's very simple. In fact, we have phase C, phase E, 80G, phase B, 600G, with a shape totally different. So what is the problem? In fact, after opening the breaker, it was discovered that there was a mechanical that was mounted in reverse. So here you can see this roll when it moves to the other side, and here it was in inverted position. So during a maintenance operation, there was a mistake. So in fact, what we can deduct of this kind of problem is that the vibro-acoustic test is really good for the quality control. It's exactly me. I compare always to when I am in, I bring my car to the garage, I got like a normal noise. And then when I take it after the end of the maintenance of my car, I just notice a problem, because the noise that I learn with my car is not the same. So when it's changed, so there is something wrong. So the sound, which is exactly like a vibroacoustic signal, it's gives us, so we learn this, what we call the fingerprint. So the finger, the signature, the typical signature, we know it, and then after we compare it to the new signature. So with this comparison, it's easy to find problems to do some. So here it's after the adjustment, the additional impact record for phase B has disappeared, then the amplitude of the phases are exactly similar. So here it's a very simple test. It's a bad synchronization of a breaker. It was done with the SNCF in France, around Paris. And then here you can see phase A, phase B, and phase C. And here you see where the accelerometers were installed, phase B and A, B, and C. Here it's the CBV with the computer, because it's a software-driven test instrument. And here, very easily, without any any mathematical processing tools, you can see that there is a difference between the three phases, and the difference was around 2.7 milliseconds. So at this time, you can confirm this test with the timing test, and then after, so you have to do something. Exactly the same case in Argentina. This is really the simplest cases where the vibroacoustic technology could be used online, offline. It's very safe to install the accelerometers on phase A, B, and C around here. You see, like on the bottom. So all the lower parts of the breakers are safe. So very easy to install. And then after, it's here you can see we got 7.5 milliseconds difference. So here it's a serious problem that has to be solved. So here we have another case where it was with the Hydro-Quebec. Why? So title is why Hydro-Quebec LG4 is choosing vibro test. So here it's James Bay, and all breakers from Alstom. So like here you have A, B, and C. For these specific breakers, to do a timing test, it's very hard to install the test cables, because we need to dismantle front panel with 32 screws. So here I have also a video where we can see how the guys is dismantling these 32 screws, and it's not easy. Well, it takes time. In fact, it's as you know, it's a heavy test. And it's hard to dismantle an inside jumper to separate contacts because like the insertion contacts is very, very low value. So in fact, it's like a real contact. And here the guy is obliged to enter inside the breaker just to dismantle this piece of metal that create the separation, you see. And also it's hard also because you need to ground the breakers on the both sides, so it's very big breakers, so you need like to do all these junction to be able to do like a typical timing test, a classical timing test. And but with the accelerometer, so it's very easy because it's done safely. So even when the breaker is online, you are not affected. So here you have phase A, phase B, and phase C. And then after, so it's easy, the timing test with the main contact only. So here here we have just done like a test to prove the concept with the timing. And here you see these different that you can see directly in the vibration. So in fact, you can do an online test on this kind of breakers and without doing the timing or a timing test or other test, just to see if the synchronization of your breakers are good or not. So it's another kind, it's of processing with the envelopes, where we confirm that the difference, like for the 5 milliseconds between contacts and the vibration give us 5.5. So in fact, the error is very, very, very weak. Another problems, it was an important leakage on phase B during a trip operation. Here it's you can see the joint which has been which was affected, which was not which was broken. And here it's just explained where the joint is located. This is like for a totally new we call this in French valve de soufflage. I'm sorry, I don't know exactly the word in English. So here it's before repair and after repair, but this is done with the study was done, the analysis was done with the envelope. And here it's what we do also when we have when we want to understand the vibration, the vibroacoustic signal. What we do a correlation between all the signals. So we take the vibration, we compare it to the motion, and here you can see this in this slide. So here you have the closed current, the motion, the vibration, and the dynamic resistance at the same time. And in fact, when you analyze, if you do a zoom of this part, so you can do an exact correlation with the motion. So when the motion starts here at this point exactly, so in fact, for the next time, you know, just if you remove these signals and these two, you can see exactly when the operation starts, and this way you can learn the vibroacoustic signal thanks to the other signals that you have done when you do all the tests all together. So it's a typical correlation just to learn your the vibration signal and how each part of the signal gives you a good information on what is going inside the breaker. So just with the sound, it's like a stethoscope exactly. I cannot say better than this. So this is typically how the how everything was connected, and it was an HPL, I think 245. Here for the vibration, how we have installed. This is the for the DRM. This is the voltage, the current, and the motion at the same time. And finally, in case 8, the last case, it's an example of 30 kilovolt circuit breaker equipped with 3 spring-loaded drive mechanisms, 1 per phase, and after 210 operations, so detection of severe mechanical anomaly. So this is the breaker. So here, typically for the exploration, because it was like a serious problem, we have installed the accelerometer inside the control cabinet. And this is the vibroacoustic signals that we got on phase B. Phase B and A used at the normal reference, and on the phase C, it was like an additional mechanical event. So in fact, why you get this this impact, you have that you don't find on A and B. So after opening, so the maintenance crew has discovered very severe mechanical anomaly consisting of, in fact, of a distorted transmission shaft in the operating mechanism. So here, if you can see between the 2 yellow lines, the distorted transmission shaft, this one in the middle. So if we can do a quick review, so it's a non-intrusive method, the vibroacoustic. It's a polyvalent method. It's an efficient method for timing breakers. It's very easy. It could detect a big variety of mechanical and electrical problems. Also, I don't have here, I didn't present some electrical problems. And it's a very good method for training analysis, because if you get always the same impact and the same noise from test to test, so just do nothing and do not open. And it's a very good method for quality control jobs. So if you have any questions, I have finished.
Okay, Fouad. Yeah, a couple of comments. One person said it was a very interesting diagnostic method. The other person, it was Andy Garbus, he said, I agree, this is an excellent concept to add to a thorough maintenance program.
To a what?
A thorough maintenance program. This is an excellent concept to add to a company's existing maintenance program.
Yeah.
And how many, my question is, how many, is that how it's used? Do we incorporate into an existing maintenance program?
Well, yes, of course, because look, in fact, just I take good examples. Well, you know, here in winter, we try to avoid maintenance, right? So we have like just between starting of spring and autumn that we do the maintenance on the breakers and transformers. So in fact, the time is very short. So what we try to do is to do a planification of the maintenance. So we have teams just to be able to do this summer, for example, only 10 breakers, only 10, not more. We have time for the maintenance, only 10. So what we do, we must have at our park of it's for example 50 breakers. We have to do the maintenance for 50 breakers. So what we can do is to try to find ways to do a quick test, a quick diagnostic test, and then after we can decide. So for example, we can do a quick test on the 30 breakers, and then at the end of this quick test, we come with only 10 breakers that are going to have like a deep test, like for the timing test, for the motion test, the DRM test, etc. So the vibroacoustic test, in some cases, it's very, very easy to, it's like a quick test, and which could be done also online. Mm-hmm. But in fact, when you do online, you have to be careful. You need to, but it could be used really as a quick diagnostic test if you know how to use it. So it's like everything, you need to learn a little, and then after you can apply it in which cases. And we have found that like for the vibroacoustic test, it could be used like a first read test, because the first read test is a quick test.
Okay, another question: how unique are the vibration signatures? Is it per equipment apparatus, or it can be used, or can it be used to diagnose a family of apparatus models?
Well, in fact, it's exactly what I have said in the first, is that you have what is nice in the breakers that we don't have for the tap changers, for the high voltage transformer, is that you have phase A, phase B, and phase C. So in fact, you have three references, and to take a decision, we need in general, one is white, the other is black. So we need to have the third one to be able to decide what to do. So for phase A, B, and C, they must be the same. If you have the same breakers, so this is the first. And the second, it's in general, when you use a family of breakers, it's always the same signature in general. So in fact, you have two tools, two references, one with the other phases, and the other one, and the other signature is with the family, the same family, the same brand, same model.
All right, here's another comment. The idea of predictive and proactive maintenance is so important, especially in this supply environment. So learning of potential issues electromechanically can help identify issues that allow time to plan a solution. I feel so few in the industry do this type of active testing. Passive offline testing does not always find the issues.
Mm-hmm.
All right, here's another question. Are manufacturers using this as part of the type test documentation?
Well, in fact, we are trying to push them to use it as to have like a typical signature when they produce their breakers.
So that's great. Thanks very much for Fouad.